Good morning. Today, I'd like to talk about an idea called fixed point iteration. This is a numerical method that's widely used in a large number of different settings. It's a slightly different philosophy than what we've been looking at so far. For a continuous function g, or at least g is continuous at all the x's we're going to encounter, we say that x is a fixed point of g if x equals g of x. Let's look at three examples of this. Firstly, g of x is x squared plus x minus 7. If there were a fixed point for this function, when I calculate the g of x, I would have to get x back for an answer. If that were to happen, it's very easy to figure out what x's we must be looking at. X is either the principal square root of 7 or the negative of that quantity. The second example will have g of x equals 2x over 3 plus 7 divided by 3x. Let's look and see if this has any fixed points. Of course, this equation doesn't make sense if x is 0, so I'm going to optimistically suppose that we don't encounter x equals 0 anytime during our calculations. I'm going to multiply both sides of the equation by 3 times x to get rid of the fractions. The resulting equation is easy to solve by standard algebra manipulations. I'll subtract 2x squared from both sides. Just like with the first function, it turns out that I have two fixed points, one positive, one negative, given by radical 7 and negative radical 7. My third example will be g of x equals x over 2 plus 7 over 2x. As before, let's see if this function has any fixed points. It's easily seen that this third g function, once again, has two fixed points. One is radical 7, the other negative radical 7. I've carefully rigged this up so that this happens. All three functions have fixed points at the same places. The technique known as fixed point iteration is this. Given some number x1, I'm going to calculate x2 as g of x1, x3 as g of x2, x4 as g of x3, and so on and so forth. The newest x number will be g evaluated at the latest x number that we already know. If g is continuous, and if this sequence of x numbers converges to something, then we can draw a conclusion. If you write down the fixed point iteration and take the limit as k tends to infinity, then the left-hand side must have a value equal to x, and the right-hand side, because g is continuous, the limit of g values of various quantities is the g value of the limit of those quantities. But our supposition is the limit of the indexed x quantities as the index tends to infinity is this number x. So, if g is continuous, at least at the x's we encounter, and this sequence of numbers converges to something, that something must be a fixed point of the g function. The connection between this and what we've done previously is, if I'm trying to solve f of x equals 0, it may sometimes be possible to rewrite that equation as a fixed point method. Then I turn the fixed point iteration loose on it. If it converges, I get my fixed point, which will be an x where f of x is 0. Fixed point iterations show up in a lot more general situations than this, but this is what we're talking about right now. I'm going to write a little program to carry out fixed point iteration for this function. I'm going to start at x equal 2 because square root of 7 is only a little bit different from 2.6, so that'll be a pretty decent starting point. To evaluate the g function, what I'll do is I'll have a separate function program unit, so that'll give us an opportunity to look into that as well. So I'll have some program statement. I'll say implicit none. I'll state that x and g are real things. I is an integer. I set x equal to 2.0. And then, just for illustrative purposes, I think I'll do 10 steps of this fixed point method. The way I'm going to calculate the g function, though, is I'll have it off in its separate program unit. I'm going to send the answer to the function, the g of x value, back in a variable called y. If I remember correctly, if you do this in the more modern way, by having a result statement, I believe I don't have to declare y in the body of this function because it already knows it. If I am misremembering, the compiler will complain bitterly about it. So my g of x value, in this case, is x squared plus x minus 7. I'll put that number into the y variable, which is allegedly the thing that's going to get passed back as the function value. Let's see if my memory is correct by trying to compile this and then running it if it compiles. Control O, enter, Control X. Never mind that MKV file. That's the file that I'm recording at this very moment. There is a file called 1.f90. The compiler didn't complain about anything. In a perfect world, when I run this, the fixed point iteration will settle down to 2.6 some odd. Unfortunately, that's not what happens. I get a -1, a -7, then I get a 35, then I get a 1,253, then I get a much bigger number than that. Then I get 2 point some odd times 10 to the 12 power, 6 times some odd to the 24 power, and then I get numbers that are so big the computer has thrown its hands up in the air and said, infinity. Obviously, this didn't work. So fixed point iteration is not necessarily guaranteed to work. To look at my second example, I'm going to be as lazy as humanly possible. I'm going to make a copy of 1.f90 called 2.f90. Then I'll edit 2.f90. The name of the program in the program header really means nothing, but if I want to be consistent about it, I'll call this program 2. Everything is going to be exactly the same, except I'm going to put in the fixed point function for our second example. In that one, the g of x was 2x over 3 plus 7 over 3x. Notice I have to put parentheses around that 3 times x, otherwise I won't be doing the order of operations business correctly. I'll save this, Control O, write out 2.f90, and Control X. The only place that I changed the program was in one line, so the only place where there could be a syntax error would be there. Apparently not, though. I get, at the very end, 2.64574456. If you look at the previous estimate, the one above that, you can see there's still a significant difference between the two. However, it does seem to be working. It seems to be settling down to a number that's about square root of 7, as it should. Again, the name of the program really isn't important, at least not at this stage of the game. In our third example, the g of x was x over 2 plus 7 divided by 2 times x. X over 2 plus 7 divided by the quantity 2x. Write it out. Exit. This time something very interesting happens. When I get to that estimate, the numbers that I'm getting back from my x iterations don't change at all. They have apparently, as far as the computer can tell, settled down to something. This is a very good approximation to square root of 7. To summarize, we've had 3 fixed point iterations. All 3 of them had the same fixed points, radical 7 and negative radical 7. One of them didn't work at all. The first one went crazy on us. The second one seemed to be working, but it was working very slowly. And this, the third one, works, and it works extremely quickly. It would be nice to have some mathematical analysis that explains this sort of thing, which will be the subject of the next video. Until then, I hope everybody has a good day, and I'll talk to you again soon.